All right. Well, it's Friday. We got survived another week. So this is a bit of a departure, and I, I think it'll end up taking two lectures to get through it. Maybe I don't know. So we'll take a look at it today. I mean, maybe we'll finish all of it. Probably not. And then next week, no class on Monday, and then we have a midterm on Wednesday. So our next lecture is 1 week from today. So, I don't know how much we retain over 7 days of of like nothing, right? Because when you're studying for the midterm, you're not going to be looking at this stuff I'm talking about here. But this is what I thought is, a fun application of MCMC stuff, of the Metropolis algorithm, I guess in particular. And so, I've kind of always, the way I've motivated things so far in the class, as I've said, in the context of Bayesian statistics, we often want to have random samples so we can do, Monte Carlo estimation of these integrals and things like that, which is a frequent thing that we have to do in Bayesian statistics. And then we particularly like the Metropolis algorithm because you don't actually need to know the exact PDF of the thing that you're going after, okay? You just need something proportional to that PDF, which is common in Bayesian stats, because in Bayesian stats, your posterior distribution is equal to your likelihood times the prior divided by the marginal. That marginal is a constant, but that marginal probability on the bottom is often very difficult to calculate. And so, if you just get something, even if you ignore that marginal probability on the bottom, the likelihood times the prior is going to be proportional to your end result, and that works out perfectly for the Metropolis algorithm. And anyway, this thing we're going to look at today is another example where the marginal probability is very, very difficult to calculate. On a practical level, I would say, either not impossible, but highly impractical to calculate the marginal probability. And so, we're just not going to worry about it. We're going to use the Metropolis algorithm as part of our way of searching out our solution. So the idea here is we are going to try to solve a substitution cipher. Substitution cipher is kind of, I don't know, I imagine you did this in elementary school, or you get some kind of puzzle where you have this, you have like a decoder key, okay? And so perhaps you have different symbols. You have like 26 different symbols. They could be little like icons and things like that. Or it might have just been the letters have been scrambled up. And so you need to have the decoder encoder key, and you could solve a puzzle like this. Or if you and a friend had the same decoder encoder key, you could send each other secret messages, right? And so if you wanted to send the message "hello friend," you would substitute H with a B, the E with a U, the L with an M, the O with an I, and so hello becomes BUMMI, and then friend, F becomes J, R becomes K, and so on and so forth, and friend becomes JKFUNO, and then your friend receives this message, and then they have to go, okay, B is right here, so that's going to be H, and U is right here, and that becomes E, and then they decode it, and you can kind of send these messages back and forth. And I don't know, when you were in third grade, you felt like you were being a spy or something like that, and I mean it's still kind of fun to do something like this, okay? And so the question is, what if you don't have the decoder key, but you just encounter the message, okay? And so this is actually the application. So I've posted in the modules, I posted this article, MCMC Revolution. This is by this guy. He's a professor at Stanford, and he was actually approached by during their kind of a consult. He was like he was approached to solve this problem. I guess in a kind of in a prison or something, in a jail, the guards had intercepted this message, okay, and they wanted to know what the inmates were passing to one another, if they were, I don't know, staging some kind of activity or something like that. So they wanted this to be translated, and so they said, well, this is because it was done by hand. They figured it wasn't going to be some complicated encryption method, and probably a simple ciphering thing, like a substitution cipher. So I want to make it very clear that this is not the same thing as encryption or decryption. So modern kind of computer security stuff uses advanced encryption, and it is far more complicated than a substitution cipher, okay? So a substitution cipher is, what you could do in third grade by replacing, one letter with another letter. But, you could do it kind of by hand, and they figured this kind of message would have a simple, simple ciphering scheme like a substitution thing. And it was just a matter of figuring out, like, which characters represented the letter A and which character represented the letter B, and so on and so forth, and that's kind of what they want to do. This is it's 24 pages, but it's a pretty good. I highly recommend the reading because it also kind of covers a lot of the concepts of Markov chains and stationary distributions and things like that. Okay, transition matrices. So reviews a lot of those things in a written document. Okay. So anyway, this is the problem that we want to try to solve. Is we encounter some kind of message, and we want to figure out what was the original text. Okay. And so if you were to give this to somebody who's kind of trained in these like deciphering things, okay, they would have strategies, and they would say, okay, you'd probably want to look for common words. You'd want to look for which character shows up the most frequently, and those will probably correspond to a vowel or the letter T or the letter S or something like that. A completely naive approach, and honestly a terrible approach to do as a human, but actually not terrible as a computer, okay? A naive approach would be, well, here's a potential key, okay, where I have just scrambled up the letters, okay? And so here's one possible deciphering key. Here's another possible deciphering key. So just imagine, I don't know, you have a bunch of these like encoding keys, and you forgot which one you're supposed to use for this message. So you go, oh, geez, I got to figure out which thing. So you take the letters BUMMI, JKFUNO, and you plug it into this thing, and you say, okay, well, the B turns into a G, and then where's the U? The U turns into a U. The M turns into a V, and the I turns into a W. And so when you decipher it, BUMMI becomes GUVVW YQPUCH. Okay, and then the other one, if you use this one, the B turns into an R, and the U turns into an A, and the M turns into an L, and so BUMMI becomes RALLPCHOAMX. And you go, oh, well, that doesn't seem right either. Okay, so you have these two kind of possible, I don't know, keys that you could use, and neither of them seem correct. Okay, and so you could throw up your hands and you go, oh, I give up. But actually, there is, this doesn't just lead us to nowhere. I mean, it might feel like, well, this is not going to work. I'm going to have to keep trying a whole bunch of these keys, and then probably, what is the probability of ever getting it correct? Okay, just by random chance. I mean, how many mappings? There'd be 26 factorial. What is 26 factorial? It's a really big number. 10, coincidentally, 10 to the 26. So I don't know. Does that even have a name? 20. I don't know. So 9 is a billion. 12 zeros is a trillion. I don't know. There's something. Okay. Nonillion, octillion, something. Okay. Some really big number. We're not going to hit it by random chance. Okay. But if we are able to somehow say, hey, you know what? This one key is better than another key. This can give us a direction, okay? If we are able to say, okay, between these two keys, this one is better, this one is worse, we should head in this direction. Now, what is the direction of keys? We'll talk about that later. But if we have a way to kind of compare one key versus another, then maybe we can use that to help us find better keys and help us eventually find the solution. And so, what is your gut instinct? If I had to say, hey, which one do you think is closer? Like, they're both completely wrong. Like, both of this is complete gibberish. But if you had to say one is probably doing a better job than the other, well, do you have a gut feeling about either of these keys? It feels like the second one is a little bit better than the first one, right? Because, like, why? Well, I mean, this is a nonsense word, but seeing the letters CHOA, you're like, well, I might have seen some words with, like, these letters together, CHOA, doesn't feel weird, whereas seeing the sequence YQP feels very wrong, okay, as far as, like, a word goes, okay? RALL, that's like, that feels like it could be a part of a real word. GUVV, I don't know, is there any word like that? Not really, right? So just our gut instinct says, okay, well, this one feels a little bit better than that one, okay? Let's try to formalize that, okay? So, here's my additional notes. Let me pull up today's view quiz. Okay, the letter A. All right. Okay. So if we want to set this up as a probability problem, okay, all right, we are what we're looking for is we want to figure out like what is the correct mapping of letters. What is the correct mapping of letters given some kind of text that we have, okay? And so what is the correct mapping given our data, okay? And I mean, it's like, how can you even write something like this? But the concepts apply here, okay? We're going to say, well, this is our posterior distribution, and this is equal to our likelihood times the prior divided by our marginal. So our likelihood is what is the probability of getting our text, okay? What is the probability of some text given some kind of mapping, okay? Multiplied by the prior probability of a mapping divided by the marginal probability of the text, okay? So, feels very strange. But when we think about the likelihood of the text given the mapping, this is going to be kind of like, okay, what is the likelihood that whatever text we decipher, what is the likelihood that this was the original message, okay? So between these two things, as far as likelihood goes, our gut is to say this has a higher likelihood that that the original message was this versus this. That's our gut feeling, because as far as messages go, this doesn't feel like it would have been a message. I mean, it could have been. It could have been like, the message I need to send you is some weird license plate I saw or something like that, okay? Versus, you know, given this mapping, this would be the text. This would be the original text. Given this mapping down here, this would have been the original text. And so we say, okay, well, what is the likelihood that this was the original message versus what is the likelihood that this was the original message? And our gut feeling says this has a higher likelihood. There's a higher likelihood that this was the original message versus this one, okay? And so that's kind of what our likelihood is referring to. You know, what is the probability of the text given some mapping? It's like, what's the probability that this was the original message? Okay. Now, the prior probability is what is the probability of the mapping? Okay. This is just going to be, I mean, as far as we have it now, we're just going to leave it as a constant. I guess prior to looking at the data, do you have any reason to believe one particular encoding key or ciphering key is more likely than another? And right now our answer is no, okay? It would seem like as far as the different possible encoding keys we have, the different 26 factorial coding keys that we have, I don't have any reason to believe that one is more likely than another. Now, perhaps, I don't know, perhaps you went to spy school or something and they say, hey, these are better encoding keys or something. Yeah, I don't. And then so they say, hey, you know, when you make a coding key, you want to make sure the vowels line up or something, right? Actually, that would be a terrible way to make a encoding key or something. But you might have some kind of thing that says like, oh, okay, we can fully expect these things to be more likely, or perhaps, I don't know, part of, you know, you encountered something and so you know like certain letters are correct or whatever, you might be able to include that into your prior thing. But as far as now goes, we'll just leave this as a constant, okay? So prior to looking at the message, basically all of the potential letter mappings or encoding keys are equally likely. And then this marginal probability, it's just what is the probability of the original text? That is also a constant, okay? It is the sum of the numerator across all of the possible mappings, okay? What is the numerator across all of the possible mappings? And as we saw, 26 factorial is a really big number. There is 10 to the 26 possible mappings. And so the marginal probability, if you wanted to actually calculate it, you would need to be able to calculate the numerator for all, whatever, 10 to the 26 mappings there are. And that's just too many. That's just too many. We're never actually going to be able to calculate this, okay? So that's what we have, okay? Yeah, 26 factorial possible mappings because the letter A can be mapped to any, So anyway, basically this has reduced down to, this is a constant on the bottom here. This is a constant over here. So our posterior probability is just proportional to our likelihood because the prior is a constant, the marginal is a constant. So we're just going to say our posterior, the thing that we're looking for, is proportional to this likelihood. So, okay. So now that we have this, is there a way for us to calculate or start talking about what is the probability of some original text given some kind of mapping? Okay, so that's what we want to, that's what we have. So we have the posterior distribution, the mapping given the text is just proportional to the text given the mapping. And how do we evaluate this? Okay. So given a potential key, given a potential mapping here, what is the probability that the kind of deciphered text was the original message, right? So with potential key 1, the deciphered text is this. With potential key 2, the deciphered text is this. And we want to say, what is the probability that this was the original message? And, again, just by kind of looking at these two things, our gut feeling, our intuition says, hey, this one is more likely to have been the original message than the other one. And I'm saying there's kind of two parts to this, okay? One way is, one thing that we're going to use to evaluate this is we're going to look at all of the letter combinations, okay? So we're going to look at every kind of 2-letter sequence, okay? And we're going to ask, what is the probability of that particular 2-letter sequence, okay? So, and so we'll have 26 letters plus a space, okay? So we will have kind of this (27 by 27) matrix, okay? So we're going to say, I think this will be my first letter and this will be my second letter. Space, and then so, what is it? This would be AA, this is AB. How often do you see the letter A followed by the letter A? How often do you see the letter A followed by the letter B? How often do you see this letter and that, right? How often do you see the letter B followed by the letter A? How often do you see the letter B followed by the letter B? What about the letter B followed by the letter C? B followed by D. So, I don't know. AA, aardvark, that's double A, right? AB, there's lots of words about. AC, lots of words with AC, I don't know, account. Okay, BA, BB, Babel, BC, I don't know. Bob, I'm sure there's lots of words, right? But then some of these things, right, like what do we encounter here? The YQ, that feels like, I don't know if I've seen that organically in a word. Or QP, right? Q is kind of like the enemy of, and not the end, like in Scrabble, it's worth 10 points, so it's not the enemy of Scrabble. But it's hard to use Q. Wait, I don't know. I don't play Scrabble, but it's just Q by itself, or is it QU? It's Q by itself? I don't know. Nobody plays. Okay. All right. So anyway, the in English, the most common two-letter this should have been a trivia question. Most common two-letter combination in English is th, because it shows up in the and a bunch of other words, and the is like the most common word in English as well. And so anyway, this is kind of our most common combination. And so we're gonna kind of go through all 27 by 27, I don't know what that is, things, and we want to try to figure out what is the probability of each of these things. What is the probability of each letter combination, all right? So when we do this, we would create our matrix. We would expect a big number for TH, and we expect other combinations like QJ to have very, very small probabilities, okay? So the way we do this is I have a script. Okay, and this script reads in, we've downloaded War and Peace from Project Gutenberg, and I should probably delete this stuff. It's like the table of contents, but in a text file, the table of contents is completely worthless, right? Like, what am I going to do with this? And this is, and actually, our script, what it does is it reads through this, and it looks at every single thing, and it says, okay, her father is very rich and stingy. Okay, and it says, okay, we're going to put in, it's going to look at every two-letter thing, and it says, okay, here I observed HE, and it puts in a tally under HE. And then it looks at, right here, it says, then we have ER, and it puts a tally for ER, and then it says R space, and it puts a tally in R space, and then space F, tally for there, FA, tally for there, AT, TH, EHE, so on and so forth. And it goes through and it's reading through these lines, and it's just tallying up, a different location in this 27 by 27 matrix. And so the computer goes through this. I mean, War and Peace was originally written in Russian. I don't know, has anyone even read this? I don't know. Do we read novels still? I don't know. Every time, I always feel like the news is always pooping on the youngest generation, and they're saying people don't read novels and watch movies, or I don't know what the deal is. But I have not read War and Peace, but I don't know, maybe. Is anyone minoring in literature or humanities or anything? Are we all just this is beside the point. I was talking with somebody who teaches at a small liberal arts college, and they were lamenting that degrees that aren't in STEM are seen as wastes of money, and I don't know. It is a little bit sad to think about it that way, right? Like, universities used to be a place where we would think and philosophize and stuff. But anyway, back to what we are doing. Okay, so yeah, if the line was sample text from War and Peace, we would put in a tally at space S, a tally at SA, a tally at AM, a tally at MP, so on and so forth. And we can go through and if you read in, and so that's what this code, the beginning part of this, or somewhere in this thing, this reference thing, it says read in the lines from War and Peace, make everything uppercase, build this transition matrix of 27 letters by 27 letters, and basically it says, for for your position in this line 1 through the number of characters, so on and so forth. The row is going to be your last letter, your column is going to be your current letter, and then basically add a 1 to it is basically what we're going to do. And so War and Peace, this very long kind of novel, this is the resulting the resulting plot. Actually, let me see if I can run this. Oh, it says it didn't find it. Okay. Session, set working directory to source file location. Sorry, okay. So how many lines of text is this? It's a long thing. It is 66,000 lines of text. Although, some of it is, okay, the license from Project Gutenberg. All right. In the first case, it was necessary to renounce the consciousness of an unreal immobility in space and to recognize a motion we did not feel. I don't know what this guy's talking about. Okay. In the present case, it is similarly necessary to renounce a freedom that does not exist and to recognize a dependence of which we are not conscious. Okay. I guess you had to read the whole thing to fully appreciate that passage. But, okay, so it's still reading through 60,000, 61,000, 62,000, 63, 64, 65, 66,000s, and, okay, so now, okay, so what we're going to also do is I'm going to just add 1 to every single space in the matrix, because if you have a 0, that means as it was reading the text, it never encountered that 2-letter combination. So like maybe QJ was never encountered, and the count there would be 0. But if you use that as a probability, then a 0 probability can become problematic, because if in your text you just have that combination QJ, and it could have just been a coincidence, and again, somebody could have been reporting a license plate, and you might have seen QJ or something, but then they would say 0 probability, so even if everything was right, suddenly that's going to become a 0 probability. So we're just going to add 1, so we don't have any zeros in here, okay? And then I'm going to do this transition probability matrix, and then let's plot it. Did this work? Okay, let's zoom. And here we go. This is what we have. So we have what we see. Can you guys see this? Okay. So here's the letter T followed by the letter H. We can see that's very dark, indicating that shows up a lot. H followed by the letter E, also very dark. You can just see like kind of the column of the letter A, and the row of the letter A shows up. The letter E, the row for the letter E and the column for the letter E shows up a lot. To kind of indicate like these are just more common letters, right? The row for Q is like hardly anything, and if there's just the ever so slightest, you can't even see it in the projection, but there's just the ever so slightest bit of a faint color here for QU, okay? But pretty much everywhere else for Q, there's nothing, okay? Similar for X, okay? E followed by X is just very light, but it's not completely blank, okay? And so on and so forth. So these are the things we see. There's a lot of words that end with E followed by a space, a lot of words that end with an S or a T, S followed by a space, T followed by a space, so on and so forth. And then this is space followed by an A, space followed by a T. So we see there's actually lots of words that start with A, lots of words that start with T and H and things like that. So anyway, that's this is our 2-letter transition probability matrix. Okay, this is actually not this particularly, but this is actually what allowed the iPhone to take off and become powerful. Okay, so I don't know how old you were, but we used to, I don't know about we, okay, but the BlackBerry phone, right? So around, when was the iPhone released? iPhone, I think, was released, I want to say 2007. History. iPhone history. 2007, oh yeah. I know electron. Okay, so our BlackBerry phones around 2008 was their height of peak popularity, and they had these little physical keyboards, tactile keyboards. Okay, you could feel the button as you pushed them. And prior to the iPhone, other companies had tried touchscreen keyboards, and everybody hated them. Okay, because it was inaccurate. Okay. These are regular keyboards. Okay, what touch? Let me see. iPhone keyboard. No. Okay, this is what we want. Okay. Yeah. So prior to the iPhone, other companies had tried touchscreen keyboards on their phone, but people got everything like. There were so many like misspellings, okay? And people preferred the physical thing because you could tell when your thumb was on the T and when your thumb was on the H, and you could feel the letters. And there were a lot fewer misspellings when you had a physical keyboard. It's just your screen was smaller, right? So Apple had a brilliant idea, okay? And they said, you know what? Okay, the problem is that people, when they touch the screen, they are not as accurate at touching the screen as they think they are. And when people make mistakes, they don't blame themselves, they blame the device. And they say, oh, my phone is so stupid, okay? But they said, you know what? After somebody touches the letter T, okay, they are much more likely to touch the letter H than they are to touch the letter G. Okay, right? You look at the two-letter transition probability matrix. After the letter T, they're much more likely to touch the letter H than they are to touch the letter G. Okay, and then after the letter N, though, okay, if you look at the row for N, they're much more likely to touch the letter G than they are to touch the letter H. Okay, so like ing and stuff like that, okay? And after N, the letter G is more likely. So, and you can try this out on your phone. And actually, I don't know, when you type on your phone, do you swipe or do you tap or do you just use voice things? I don't know what you do. But if you were to type, okay, and you could try this out on your phone, you could pretend to send yourself a text message. Intentionally tap. I want you to type out the word thing, okay? But when you type the letters, intentionally after the letter T, intentionally touch the space between H and G, okay? And after you type the letter N, intentionally touch that exact same spot between H and G, okay? The border between H and G. And what you will see is that your phone should correctly get it and will type out THING and will not do a misspelling. Okay? Is it working for you guys? Okay? And that's because what's happening underneath, even though the screen doesn't change, what's happening is after you tap that letter T, the size of the keys change. It's invisible. You don't see it. But the size of the keys change. The letter H becomes bigger. Okay? And so the area of the screen that gets mapped to the letter H gets bigger. After you tap the letter N, the area of the screen mapped to the letter H gets smaller, and the area for the letter G gets bigger. Okay? That was the huge insight behind the on-screen keyboard, is that they said, hey, you know what? These letter combinations, some of them are much more likely, others are much less likely. And so after somebody touches the letter T, if they touch that space between H and G, even if they touch a little bit onto the G, let's make it an H, okay? After they touch the letter N, even if they touch a tiny bit in the H and G, or the space in between H and G, let's make it a G, okay? And that greatly improved character accuracy, okay? Typing accuracy on the on-screen keyboard. And that allowed basically on-screen keyboards and iPhones to become popular. And now it's hard to, like, it's very hard to find a phone that doesn't have an on-screen keyboard, okay? And then we further improved things with like actual words and word prediction and things like that. But the big insight for like just typing out your letters was kind of this thing, right? So that's my cool little party trick when people say like, oh, statistics and data science, what do you do there? And you say, well, let me pull out your phone and do this, right? Because it's kind of a neat thing, because you don't think about it, because the screen doesn't change, but the mapping of what part of the screen changes. So okay. So anyway, so we have this, and so now we can use this to evaluate. Okay, so I typed in the thing there. We can use that to evaluate our text. So we look at this and we say, okay, what's more likely, C followed by H or Y followed by Q? And we can go through our transition matrix and we can say, oh, C followed by H, that's kind of common, okay? Y followed by Q, never happens, okay? And so we can use that and go through kind of our translated text or deciphered text, okay? And just say, hey, which one of these things are more likely? Okay, so that's going to be one way to evaluate what is the probability of our text given some kind of mapping. Okay, the other thing is, let's say as we start to do these things, we like words start to appear. Okay, if real English words appear in the message, like that's a good sign. Okay. So what we also want to do is we're going to say the probability of our text given some kind of mapping, okay, is we're going to get kind of the probability of those two-letter combinations, but we also want to bring in the probability of real English words, okay? And so if your text, you're deciphering, if you have like kind of some three-letter combination, and it deciphers it into THE, the word the, we'd say, hey, you know, that makes sense, okay? Because the is the most common word that we see. And so we also, I have this thing called the lexical database, okay? Let's load that up into R. No, that's not that. How do I load it? Okay, load the file lex data. Okay, so this is just kind of a listing. I forgot where I got this. I want to say from Wikipedia or something. And so they just have a whole bunch of words, and they have kind of the relative, some relative probability. I'm not 100% sure how they calculated these things, but it's like, okay, I don't know what these words are, right? Like, okay, so abate has a relative probability of 2.6 times 10 to the minus 6. Okay, abated is apparently a little bit more common with a relative probability of 3.8 times 10 to the minus 6, okay? And abatement is less probable with a probability of 1.27 times 10 to the minus 6, and abatements is 9.7. Okay, so here, let me see lexical database $ word. Wait, how do I get this? Okay. Which is equal to, I don't know, the 81073. So, okay, so we'll do lexical.database $probability is square bracket to this. Okay. All right, so that's the relative probability of the word the, and I don't know, what's other what's another word? I don't know. Okay, common words. What are some common words? Okay, the word 1 I think is pretty common. 1 has a probability of 0.0028 versus the word 2 shows up only 0.001, and 3 less probable, so on and so forth. What do you think is more common, 3 or 10? I feel like my gut instinct says 3 is more common than 10, but I don't know. Yes, 0.005, 0.0018. What about 10 versus 9? I'm just curious. I feel like 10 has to be more common than 9, but I don't know. Let's see. Oh yeah, now we get scientific notation for that. Okay, so what about 100? Okay, so 100 is more common than 100 is more common than 10. Look at that. 10 is 0.0018, 0.00027. Okay, well anyway, so you can go through and look for all of these different words. There's 92,000 words in here. I don't know. Okay, so anyway, that's what we have there. And then what we're going to do is we will go through and evaluate our text, and we'll see. Okay, if we encounter real words, we'll factor that in. Okay, so the total probability though, it's a little hard, right? You have to probabilities are generally products of things, or like we have to kind of mix some of these things together. So we're going to have a scaling factor lambda, and this will allow us to control, like, we have these kind of slightly competing priorities. I mean, oftentimes they will work together, but they might come to a different thing. And, we might say, like, which one's more important, the 2-letter combinations or the real English words? And so we have this this value lambda that can say, hey, you know what, weight this thing more importantly, so that if we encounter real English words, then that should be heavier weighted versus, or maybe weighted less or something, okay? So that will go in there. And so we'll use this as a way to kind of evaluate the probability of our text for different mappings, okay? And so hopefully that will align with kind of our intuition about some of these things, and this will give us a direction as far as uncovering the correct mapping. So you'll have to wait a week, and we'll apply it, and we'll put it into the Metropolis algorithm to evaluate this. Okay, I've given you just one answer so far. Okay, so your other 2 answers for today are the letters C and D. C as in cat is your second answer. D as in dog is your third answer. Okay, we will end here. Have a good weekend. Good luck as you study, and I will send out a seating chart. And so the next time I'll see you will be Wednesday in here for the midterm exam. All right?